We are ready now to present some image deblurring results. First, let's talk about the parameters in our scheme. These are the equations we use for the iterations, be it the steepest descent or the ISTA. For both, we include here the acceleration. We already saw that the SD step size is related to the eigenvalues of the Hessian of the function we are minimizing. We will show how to set it up using the par method. The same goes for the parameter C in ISTA. The par method is used to fix it, and we'll discuss it next. Lambda was set manually to be 0.06 so as to get the best deblurring we can get. Last but not least, the acceleration parameter m. It is set to be either 0, no acceleration, or 0.9. Both C and mu depend on the maximal eigenvalue of the matrix HD transposed times HD. How do we evaluate this eigenvalue? The answer is the par method. This algorithm starts with a random vector and iterates, normalizing it and then multiplying it by the matrix of interest. Note that in this multiplication you want to avoid the calculation of the matrix HD transposed times HD. You do so by first multiplying the vector vk-1 by HD and then multiply the resulting vector by HD transpose. This way only matrix vector operations are done. This explains the parenthesis in the equation. After enough iterations, 100 in our case, the inner product between Vk and Vk-1 is an estimate of the maximal eigenvalue. Okay then, let's see the various algorithms in action. First, we show the value of the function f of alpha as a function of the iterations. 4 curves are shown, the SD and the ISTA in their accelerated versions. It is clear that ISTA and FISTA are more effective, leading to a faster descent. The curves suggest that 1000 iterations are not enough and we could get more by continuing the process, which is in fact true, and we'll come back to this. Remember that the minimization of f of alpha is only the means towards an end. What we really want is a deblurred image. The graph shown here presents the quality of the image as a function of the iterations for the 4 algorithm versions we test. We measure the goodness of the image by the ISNR measure. In the nominator, we have the error between the given blurry image and the ideal one. This would be the error if we do nothing. In the denominator, we have the distance between the estimated image, d times alpha k, and the ideal one. So this is the error of our suggested solution. Thus, the bigger this ratio, the better the outcome. We take 10 log 10 of this ratio, so if the ISNR value is 0, this stands for a ratio of 1. Implying that we are getting a result as good as doing nothing. Any value above 0 is an improvement over the given image, and as can be seen, we get an improvement of about 7 dB after about 60 to 70 iterations using the accelerated methods. However, if we proceed, this gain deteriorates. By the way, just in case you are wondering, there are automatic techniques to know when to stop in order to take the best possible result, and they perform rather well. One last comment. Remember that we said that lambda was tuned to get the best result? This is what we meant. We modified lambda to get the highest possible peak as seen here. Now let's look at the images we got. The algorithm starts deliberately with a 0 image, which gives a very negative ISNR value. And now we iterate and the result improves and improves. There are some halo artifacts, but those vanish as we proceed, till we get to the 59th iteration, which gives the best image in terms of ISNR. And we have to say, this result looks quite good. For your information, more recent deblurring algorithms, also relying on SparseLand, but in a very different way, get an ISNR of around 10 dB and beyond for this specific test.